All right, I'm back. We're in the middle of page 315, and we just kind of like figured out where some functions were increasing because that's what we were supposed to do. We checked them on our calculator because that's what we were supposed to do. And now what we're going to do is talk about some stuff that we already kind of know, but we're going to make it a little more formal. So first up, a sign change. So you've probably never really thought about these before. A sign change is when a function changes from positive to negative or vice versa. So from negative to positive, also an option. Sign changes are really important when you're looking at the graphs or sign charts for first derivatives, and for second derivatives, we'll find out. But the reason they're super important on the sign chart or the graph of the derivative is that those are going to be the locations of maximums and minimums. We already know this because we've been doing it a lot. We talked about it just in the last video. This is called the first derivative test for relative extrema. All the things that are called derivative tests are actually for relative extrema. So there's also a second derivative test, which tells you about relative extrema. So first derivative test, this is a big one. I'm going to highlight it. I'm going to go around the edge, I guess. Can I do it in one continuous thing? It's about as straight a line as I can make. So you're probably a better highlighter than I am. Okay, so first derivative test for relative extrema. Assume that f of x is differentiable. Let c be a critical point. So critical points, obviously super important. That's why they're called critical. Critical point of f of x. If f prime changes from positive to negative, so in your mind, parenthetically think f of x therefore changes from increasing to decreasing, then f of c is a local maximum. If f prime changes from negative to positive, parenthetically in your brain, f of x changes from decreasing to increasing, then f of c is a local minimum. That's all it says. So we need sign changes. Not all sign changes, not all critical points will have sign changes, but all sign changes at critical points will be relative maximums and minimums. So that just keeps coming up, that whole like if then, and then like the contrapositive is true, but the converse isn't necessarily true. Whatever, go back and review that, probably geometry, hard to say. All right, so this can tell us where we have relative maximums and minimums. And that's a huge deal because like, we're very, very focused on trying to do that. All right, let's see if we can do this problem. The function f of x is differentiable on the interval from 0 to 10, except at x equals 4. So differentiable everywhere except at x equals 4, which if I didn't read further would tell me that the function's continuous everywhere except at x equals 4, where I don't really know if it's continuous. But then you keep reading, but it's continuous at all points on the interval. So from 0 to 10, function is continuous, it's just not differentiable at x equals 4. Why might that happen? You could have a corner, you could have a cusp, right, which is where the slopes are infinite and negative infinite on like either side. There's no other reason that I can think of, so that's what's happening. So function is differentiable for everything except, oh, it could also have like a x to the 1/3 type sich. So it could do this, where it like goes vertical for one instant. That's not a cusp. That's not a corner. That's actually a point of inflection, which we'll talk about more later. But these are, when I read a problem, I try to think of like it's like Dr. Strange trying to think of like 10, 100 billion scenarios. Like I read it and I'm like, what could this mean? So function is differentiable everywhere except at 4, continuous everywhere from 0 to 10. All right, good deal. All the critical points are in the table. That's key information because if we don't know that, we kind of like, you can't make any assumptions at all. DNE stands for does not exist. Always the case, but sometimes you got to spell it out. All right, let's see. So we have this table and we want to state the critical points. All right, critical points are where the derivative is equal to 0 or the derivative doesn't exist. So I'm looking at this and I see a does not exist and I see a 0. Okay, so those are going to be my critical points. So I'm going to say x equals 4 is a critical point, because f prime of 4 does not exist. And x equals 4 is in the domain of f of x. So do I really need to say that? I don't know. I always worry that I'm under-explaining and then I end up over-explaining. Don't use too many words, but make sure your explanations are like locked down. Nobody could complain about this. X equals 4 is definitely a critical point. Why? Because f prime of 4 doesn't exist. And then somebody's like, well, what if it's not in the domain? Oh no, and x equals 4 is in the domain. So we covered everything that we wanted to, and we got it. So where the derivative is 0 is a little easier because we can just say x equals 7 is a critical point because f prime of 7 equals 0. If f prime exists, it means that the function must exist at that point, because if function's not, if a function's differentiable to a point, then it's continuous. If it's continuous, then the value of the function must exist. So like that's a much more contained explanation, and it's why everyone just prefers the derivative to be 0 instead of doesn't exist. But like, you know, whatever. All right. Find all values of x at which f of x has a relative extremum, which means a relative maximum or a relative minimum. All right. Determine whether f has a relative max or min at each of those values. Justify. All right. So we got to look at the table, and we got to look for sign changes at critical points. So what should I use? I'm going to use red for decreasing, I think, and then blue for increasing. I don't really know. All right. So f prime changes from negative to positive at x equals 4. F prime changes from negative to positive. F changes from decreasing to increasing. F actually has a relative minimum at x equals 4. So let's do that. Let's say that's true. So here we go. F of x has a relative minimum at x equals 4. Now we want to say why. So I'm going to say because f prime, or you could say f prime, I'll say f prime of x changes from negative, so I'm going to abbreviate negative as just neg, to positive POS at x equals 4. Okay, relative minimum at x equals 4. Why is there, so it's like you're always on trial, and you're the witness, and you have to make your statement, then you have to defend it, because somebody's going to ask you a follow-up question. So you can't just say f of x has a relative min at x equals 4. As soon as you say that, the math lawyers are like, why? Why does it have that? And you're like, whoa, because f prime changes from negative to positive at x equals 4. Done. No complaints. All right, so now we're positive until we get to 7, and then after 7, still positive. So that's interesting. I was expecting there to be a relative something there, because if the derivative is 0, you might get a sign change in the derivative, but we went positive to positive, so that's it. So that's a little disappointing because I wanted to write another description, but you know, what are you gonna do? All right, so what's the next question? True, false, maybe. So I don't write great questions, so in my experience, the answer to these is often just maybe, because like I didn't consider the 300 trillion potential scenarios when I wrote the question, but let's see. True, false, or maybe, f of 7 is greater than 8. Justify. F of 7 is greater than 8. Justify. All right, so I think, I don't know what I was thinking when I wrote this. The answer to this is definitely maybe. So here's my reasoning. So let's just write maybe. Maybe. So why is it maybe? Well, look at everything that we know. We know the function's differentiable. We know that the derivative doesn't exist at 4. We know the function's continuous at all points on the interval. All we know are values of the derivative. We don't know any values of the function. For all we know, this function lives at, between y equals 1,000 and y equals 1,000,000. There's no way to know. We don't know anything about the actual values of the function. So I think this question is trying to confuse you between f and f prime. F prime, like, I don't know how you would make an argument about that either, actually, in this case. Well, f prime of 7 is definitely 0. It's just in the table, but maybe. So we don't know anything about values of the function. All we know are things about the slope. So values of f of x. So we haven't talked about this that much, and we probably should. Vertical shifts, I remember talking about this in some video, I don't know which. Vertical shifts of a function do not change the values of the derivative. So if you had, f, let me just, so this is, it's related but unrelated. Like I'm just going on, I'm just educating here, right? Like I'm not stuck on these notes. We can talk about whatever we need to. So if we have f of x equals whatever, I don't really know. Let's say we have f of x equals x squared, and we have g of x equals x squared plus 32. Well, then f prime of x equals 2x. G prime of x also equals 2x. So f prime of x equals g prime of x, even though all the y values are different, right? But they differ by a constant. They are always a constant difference apart vertically, which means the slope is going to be the same. So we don't know anything about the values of the function, so we cannot say if f of 7 is greater than 8, less than 8. I don't really know what that question is talking about. Okay. True, false, maybe. F prime of 8 is less than 8. F prime of 8 is less than 8. F prime of 8 is less than 8. Okay, so this one's a little, it's a little less clear, but like, I don't know, depends on how you're thinking about it. So if you notice, F prime of 10 is, oh my God, that's not a highlighter at all. F prime of 10 is 8. So I think what they're trying to do is they're trying to get you to think, they being me, I wrote the notes, but f prime of 10 is 8, and we know that f prime is positive between 7 and 10. I feel like they're trying to confuse you again with like the prime versus the regular function. So this, again, we're going to go with maybe. So let's say maybe. And I'm going to say all we know is that f prime of 8 is definitely positive. We don't actually know anything, right? So if you were going to graph f prime, I need f prime of 7 to be 0, I need f prime of 10 to be 8, and I just need f prime to be positive in between. So if this is a graph of f prime, then at 7, I need to be 0. At 10, I need to be up at like 8, 10, 8. And then, I could do like really, you could just do anything. Like, there's no way to know, right? Like, all we know is that it's positive on that interval. We don't know anything else. So these are just like things to think about. As I mentioned, going into these problems, when I rate these like always, sometimes never type problems, like the answer is almost always maybe, because I just didn't think it through ahead of time when I wrote the problem, and then I realized like, oh yeah, there's like all these other scenarios. But you need to think about all those scenarios too. So it's not really a bad thing, I tell myself. But I'm going to wrap this up here. I'll be back in the next video. I hope you are finding these helpful, and I will see you then.